Hi everyone, welcome back to the channel. So for today's video, we're going to start talking about energy, okay? And energy is a measure of how much change a system can cause, right? Sounds a little bit vague, so let's explain it. In the most general sense that you can have, the change in energy of a system is equal to heat plus work, right? We've learned a little bit about work. We haven't learned so much about heat. So we're going to ignore this general equation for now. This is just something to keep in mind for later on down the road. So an important thing to keep in mind about energy is that it can't be created or destroyed, right? It's basically what we call conserved, right? Again, can't be created, can't be destroyed. And what you get is from that, you get this big old, this equation that says that the change in energy of the universe is equal to the change in energy of any system that you define and the change in the surroundings. So everything outside the system. If you call this bottle your system, everything else outside is the rest of the universe. And it's always going to be equal to zero because, again, energy can't be created or destroyed. Now, energy exists in various forms, and this will help you kind of understand what this kind of vague term energy really means. You can have mechanical energy, which moves something, right? And then you have chemical energy, which is in chemical bonds. You have energy in circuits that power your phone. You have energy heating things up, which is heat energy, right? And you have nuclear energy, which is when you split an atom, which is fission, or you combine atoms, which is fusion, right? Now, these right here, 1, 2, 3, 4, these bottom four are outside of the scope of this class, at least currently. So we're going to focus on mechanical energy. And now we can look at the equation for mechanical energy. The total mechanical energy of a system is equal to its kinetic energy plus its potential energy, right? And we haven't touched on these two yet, but we're going to get into it in just a minute. So what you see is that if delta E of the system is equal to 0, that means no energy is lost. The energy is just maintained in the system, right? That's conservation of mechanical energy. If the delta E of the mechanical system is not equal to 0, energy was lost. And keep in mind, being lost doesn't mean that it disappeared, right? It just means it moved into a different form, right? If it was mechanical energy, if you have a ball rolling down a hill, right, and there's some friction acting against it, what you get is, or let's make it even easier. If you grab your hands and you rub them together, right, you form, there's friction between your hands, right? And you feel some sort of heat if you keep going, you get heat. That heat is a form of energy as well. So the mechanical system only deals with kinetic and potential energy. And so when you look at the system and you're like, hey, it's losing energy somehow, right? It's usually in the form of heat or in the form of some other form of energy, right? So just keep that in mind. It'll make more sense as we move along. So again, I just said it right now, but since it can be created or destroyed, it can be transformed from one form to another. But the total amount of the energy in the universe is going to remain 0. And so let's fix this. The change in energy of the universe minus the change So we go back to our energy equation that we put above, that delta E of the universe is equal to energy of the system plus energy in surroundings, right? And it's all equal to 0. I just wanted to place this here one more time just because it's very, very important that you understand this. And so let's take a look at the side note. Again, if delta E of the entire universe is always zero, right? There is no change in energy of the universe, right? What you get is that if delta E of a system, right, like this water bottle, if the change in energy here is not zero, then it's balanced out by the surroundings. And so I'm going to give you an equation here. Remember, delta E of the universe is equal to this delta E of the system plus delta E of the surroundings, and it's all equal to zero. So if delta E of the system is 10 joules, right, then the delta E of the universe again is going to be always zero. Then what you have to do is basically the delta E of the surroundings has to cancel out the energy of this bottle, right? So if this is 10 joules, everything else outside would be taking out 10 joules so that the overall balance of the universe remains zero. And so you get that right here, delta E of the system is 10, delta E of the universe is 0, and so delta E of the surroundings is negative 10 joules because it has to cancel out the change. So now we're going to get into the topic of conservative forces and non-conservative forces. This has a lot to do with energy and work, so I want to make sure you really understand this aspect, right? Conservative forces have work based on displacement. So a conservative force, again, it does work, but it's always based on the displacement, right? We're going to get into this term path independent in just a little bit. But what it's saying is that a conservative force, if only conservative forces act, energy doesn't leak. The delta E of the mechanical system, the overall energy of the overall mechanical energy change is zero. And so it has potential energy, and we'll explain what that means. To make this more concrete for you, here are some examples of some conservative forces. Gravity, the electric force, the spring force. Those are three different forces that are conservative, right? And we'll show in the diagram why they're conservative and why they are the way that they are. So I want you to remember the idea of conservation of energy, right? Energy can't be created or destroyed, right? And so when you look at this diagram, you have you have a path from A to B. You're trying to get from here to here, right? And you're an object and you have some mass, right? Let me just draw the object for you. There's an object with some mass, right? What happens when an object is on a ramp like that, right? Assuming there's no friction. The only force that's acting on it is going to be the force of gravity based on its mass. It's pulling it towards the earth. And so that's why I drew this mg line over here. But remember that work is force times distance. And so over here at the top, there's no work being done at all on this box, right? It's just there. But the second after it starts sliding down the ramp, work is being done for the entire duration of time, from here to here, which we'll say is that delta x is going to be equal to h, right? And so what you get is that if there's work being done here, and there's work being done this entire period of time, but there's zero work being done at the beginning, remember how work is related to energy, right? You need energy to do work, right? Just like in a colloquial sense, like if you think about it, you need energy to go to work every day, right? Same thing with everything in the universe. It needs to have energy to be able to do work. And so if work right here is zero, and there's work being done this entire period of time right here, right? What you get is basically either two things could have happened. Either work was zero here and energy was zero, right? If we say work, you need energy to do work. So if work is zero, we can just assume, oh, energy is zero, right? But for this entire duration of time, work equals something, right? Let's just call work, let's use a different variable. Work is equal to L, just to make it simple, right? Work is equal to L for this entire duration, right? And so energy is equal to some value. Let's just call it M, right? This is just to make it easy on you. Instead of a variable, we'll just put a little hashtag, right? Just to show that it's a number. So if we all understand how you need energy to do work, and there's no work being done at this initial point right here, but there is work being done the instant after this point, what you can have is either one, no energy was present, and then after this specific point, energy just popped into existence, right? I want you to try to think about it. Is it option one, there was no energy at the start? Or was energy always there? At the start. So if work is equal to zero at this point, was there energy? Or like this entire time, there was energy throughout the entire duration of time, even though there was no work being done? Or after this point, was energy popped into existence right after that specific point, and so you have energy throughout the rest of it? So I want you to try to pause the video and really come to a decision, and let me know down in the comments what you thought, and I'll go over it right now. Okay, so what you see is this is not possible. Energy could not be zero at that point because of conservation of energy. Energy cannot pop into existence after the object starts to move, right? Or for the object to start to move. Gravity this entire time is acting upon the object. And so when it's at this height, work is zero because gravity hasn't been able to move the object, right? It hasn't been able to pull it down. But what you get is there has to be energy here in order for the object in order for gravity to do work on this object, there had to be energy at this initial point. Because, again, you can't have energy is equal to zero here and then energy is equal to something here, right? It wouldn't work out. And so what we say is that since there was energy here, but it wasn't moving, let's call it potential energy. It potentially could move, but it does have energy. And so that's what we came up with, is this term of potential energy from this idea right here. And so now let's figure out what that means mathematically. Remember, the work done by gravity is equal to the force times distance cosine theta, right? And so theta is just going to zero because gravity is always down like this, and motion is going down. And so what you get is motion and the force are acting in the same direction, so there is no angle between them, it's just zero. When you put cosine of theta as cosine of zero, it just becomes 1. And so what you get is force times distance. What's the force being acted? It's mg. What's the displacement? It's h. So work done by gravity is equal to mgh. Now that makes sense, we need to think about a curved path, right? How does gravity work on a curved path? It's the same thing, because it's always acting down. The motion is going to overall as an average go down. And so the angle between them is zero. There's no difference between the force acting and the motion, right? Of course, you can use calculus to derive this a little bit better, but just think about it. On average, the object goes from point A to point B. It's just going straight down. And the gravity is always going to act straight down. And so since there's no difference in the angle, this would just become 1. So again, we get work done by gravity is equal to mgh. That's where that term that we talked about earlier, path independent, comes in, is whether you have a curved path or you have a straight path, right? They're both equal. The work done by a conservative force is not going to differ between a straight path or a curved path, as long as, of course, it's only based on the displacement, right, between point A and point B. As long as point A and point B are the same distance of displacement apart, what you see is that whether you go like this to get to path B or you go straight, it's path independent. It doesn't matter, right? It's going to work the same way regardless. Now we have to get into what we call non-conservative forces, the opposite of conservative forces, right? For these ones, work is based on the distance. They're path dependent, right? So in this case, energy does leave. It leaks, right? The change in energy of the entire mechanical, the mechanical energy is not equal to 0. So there isn't any potential energy, and we'll get to the reason in just a second. Here's some examples of some forces that are non-conservative: friction, tension, and applied force. Let's look at our diagram, right? When you have friction acting and you have this object right here that wants to go down with some mass, right? What you see is now that you introduce friction, friction goes against the motion, right? Motion wants to go this way, friction's acting against it. So there's that issue right there. And what you see is that there is an angle now. There's 180 degrees between the two. They're complete opposites, right? The 180 degree angle. And what you get is now it's equal to -1. Cosine of 180 is equal to -1. So force is the force of friction. So the work done by the frictional force is equal to negative force of friction times h on a straight path, right? And now we get this equation that tells us how work is done in a system with friction acting upon it, right? So we need to figure out, well, how does it look with a curved path, right? Now with a curved path, this distance, the entire distance is L, which I wrote over here. The displacement remains h, right? There's no difference in point A to point B. They're the same points, right? But a different path. This path is slightly longer, right? And friction is going to act along every piece of the, it's going to act as the motion occurs. It's always acting against motion. So at every single point where the object is moving, friction is acting against it. And what you get is that, again, on average, since they're going like this, there's that angle of 180 degrees. And so what you get is, again, force is the frictional force. D is now going to be different, right? Remember, the negative comes from cosine of 180 being -1. So you get very, very similar equations, right? But there's a big difference. Over here, we used h, which is the displacement. Over here, we had to use L, which is the length. In a curved path, the distance and the displacement are not the same. In this path, the straight one, distance and displacement are the same, so it doesn't matter, right? But when you get to a curved path, it does matter. The length is not equal to the displacement. And this creates a difference between friction acting on a straight ramp and a curved ramp, or this, like a curved line, right? Curved path, I apologize. And so what you get is now, since they're not the same, this would be path dependent, right? Non-conservative forces, it does matter what the path looks like, whether it's straight or it's going back and forth and zigzag, etc., right? It's not based on the displacement, it's now based on the distance. That's how those two differ from each other fundamentally.